Hello everyone, welcome to Pre-Lecture 24. In this lecture we're going to be talking about kinetic molecular theory, or basically how gases move. So, if you remember from last class, we talked a lot about how gases behave ideally and the ideal gas law, where our pressure times our volume is equal to the number of moles times our ideal gas constant R times temperature. And we're going to basically continue on that and start to think about, the ways that gases move around and how that might inform our understanding of the ideal gas law. And so the main tool that we use to do this is called kinetic molecular theory. This is a set of observations, things that we might call postulates, that explain how gases behave. And so the assumptions that we have here are that gases are composed of a large number of particles that behave like hard spherical objects. They're in constant motion, and that motion is random. Basically, there's no coordination to the way gas particles move unless you get something like a bulk wind, but at that point it's weather basically. It's not just gases. Okay? Postulate number 2 is that these particles move in a straight line until they collide with another particle or the walls of a container. That is to say, gas particle moves until it is hit by something or hits something else. The particles themselves in a gas are much smaller than the distance between our particles. That leads to our property of compressibility in gases, right? And that means that most of the volume in a gas is actually just empty space. Okay? Postulate number 4 is that there is no force of attraction between gas particles or between the particles and the walls of the container. If they were attracted to each other, essentially they would start to glob onto each other, condense, and eventually turn into a liquid, which can of course happen under certain conditions, but as long as things are remaining a gas, they are not going to be attracted to each other. Postulate number 5 is that any collisions between these particles or the walls are going to be perfectly elastic. Essentially a conservation of energy where we can transfer it between one particle to another or to the walls of a container, but our total kinetic energy has to be the same. And then finally, our average kinetic energy of a collection of gas particles will depend on the temperature of the gas and nothing else. And so our temperature is going to be the thing that is directly correlated with the average kinetic energy. And that is where we're going to talk about the rest of the pre-lecture. Okay? So at any time, our gas particles are moving at a certain temperature, and that means they will have a average kinetic energy. We can calculate that by taking 1/2 of the mass of our particle, generally our molecular weight, multiplying it by the velocity of the particle squared, and that's typically in meters per second, right? As our temperature increases, what happens is that the average velocity of our particle increases. So if we look at a lower temperature here, our average kinetic energy would be lower at kind of the top of our peak. Whereas when we raise the temperature, our average kinetic energy goes up. So even though there might be less particles with that exact number or that exact amount of kinetic energy, it overall still increases, and we actually get a greater distance between our slowest particle and our fastest particle because we have a statistical distribution of those gas particles, and the more energy they have, the greater that distribution becomes. Okay. Because our mass is one of our components of kinetic energy, and we often want to compare gases to each other, the smaller a gas molecule is, the faster it will be moving on average. And so we can actually, of course, quantify that relationship through this equation, which is ultimately derived from our kinetic energy equation, where the velocity of one molecule is going to be inversely proportional to its molecular weight, And if you remember, our velocity terms had a squared in our kinetic energy equation. So if we undo that, we end up taking the square root. So this basically lets us calculate the average velocity of a certain molecule if we know the other velocity and molecular weight of a different molecule. Okay? And because smaller molecules move at different speeds, people have done some very clever experiments to come up with relationships for how quickly a gas will diffuse. That becomes very important for certain applications that I'll mention here in a minute. But essentially, our rate of diffusion is going to be proportional to 1 over the molecular weight. And there are going to be some different constants that we have to factor in here that have to do with our medium, as well as the pressure, but we're not going to have time to go through those in this class, but if you take some upper division chemistry, you may talk about them. And as you can see here, if we basically graph the time it takes for a molecule to travel a certain distance, there's a linear correlation if we graph it against the square root of the molecular weight. Okay? And this becomes important for things like perfumes. So there's a lot of chemistry that goes into making scents and perfumes. And so these are some of the main molecules that are in something like rose oil, which is, of course, very fragrant. And you'll notice that these molecules are actually relatively large. So if we think of our gas molecules having typically a mass lower than 70 AMU, all of these molecules have an AMU over 70. And what that basically means is they move quite slowly because, of course, if you put on a perfume or some sort of scent, you don't want that scent to go away within a few minutes. You want it to last most of a day, right? And so those molecules are actually mostly liquids at room temperature, but then evaporate as the day goes on slowly, so that if you put on a perfume, you can smell nicely all day instead of just for a few minutes. Okay? So that's going to be our pre-lecture for today. We're going to do some more practice problems in class, as well as talk about deviations from our ideal gas laws. Hope that was informative. If you have any questions, of course, let me know. Otherwise, have a good day.